we start? Okay. So Matt is going to talk the finding the missing baryon and maybe concerning the cosmology with FRBs.
Right.
So the tenor of this talk is a bit different than the previous ones. And so I'm mostly going to focus on what I think is a really interesting question. So I'm going to try to convince you that it's, using FRBs to figure out where the baryons lie in the universe is something that seems within sight. I wrote a paper about this about 5 years ago after the Thornton paper finding a sample of these FRBs, and I've been kind of watching the field since. And usually, when you write a paper a while ago, and with time you kind of become more pessimistic about the prospects for it actually working. And I think this is actually the case where it's the opposite. I mean, I think until earlier when after a wavy comment I deleted guaranteed science, but I think it's pretty close. I think like with the sample of bursts that are that time and mass gap and other efforts are going to have in the next few years, this is science that's within reach. All right, and then for the very last part of the talk, I'm going to talk about cosmological parameters and what has to go right for us to be able to use FRBs as cosmological curves. And then at the very end, I'm going to just quickly, because there was kind of this spate of papers in the literature claiming that you can measure dispersion to non-variable sources a few years ago. I'm just going to give a two-sentence proof of why that's not the case. Okay, so you guys all know that the universe is mostly dark, like dark matter, dark energy, but it's also the case that the baryons are most of the baryons we can't see. So they're not in the galaxy, they're not stars, and so let's say if I took a galaxy, so this is the Hubble ultra deep field. This is a few minutes on the side, and most of the baryons that are associated with this galaxy, with the dark matter of this galaxy, resides on a scale that's much larger than the size of the galaxy, like roughly 30 times the size of the galaxy. And so if I drew the dark matter halo for this galaxy, it would look something like this on the sky. And we think that a lot of the baryons, much more that are in the galaxy, are on this type of scale. If I choose another galaxy, this is an elliptical galaxy, probably a little bit more massive. Maybe this is the dark matter halo. And then I can keep doing this. There are a lot of galaxies in this image, and so I can keep proceeding. And one thing to note is just that these dark matter halos overlap. So like if I chose a point in this image, it's likely not going to hit a galaxy, but it's going to intersect. If I send a skewer through the universe, it's going to intersect a lot of dark matter halos. And we think that on the scale of these dark matter halos, this is where a lot of the cosmological baryons are.
So where are the filaments and the voids and all those jazz in the circuit? Where is this one in the broad screen, please?
Yeah, we wait a few slides. Okay. And so so one thing I'm going to argue, just to convince you why this is interesting science, is we really don't know. I said that the baryons are kind of on the dark matter halo scale, a lot of them, but we really don't know this. And so if I just took 10 to the 10 solar mass, which is the Jeans mass, 10 to the 10 solar mass dark matter halo, which is the Jeans mass for the universe. So above that mass, the halos are able to pull in the gas. And I asked how much mass is in halos above this at redshift 0. You compute a number that's like 50%. So half of the halos in the universe are massive enough that they can pull in the gas. And it also turns out that in these halos, except the really, really, really big ones, which contribute a very small fraction of the mass of the clusters, this gas can cool in a very short fraction of the universe. And so you might expect that 50% of the baryons lie in these halos that can cool and form stars. That 50% of the baryons are stars, and that's just not not correct. It's really something like 4%. And this is because of feedback processes. Namely, when stars form, they put in a lot of energy and die soon via like supernova and other processes. And also for high mass galaxies, we think of the black holes in the center of the galaxy are also and in fact, you could do this if you assume that the most massive galaxies are the most massive dark matter halos. Then you can map the stellar mass of the galaxy to its dark matter halo mass. This is called abundance matching. And so you can and then you can plot the ratio of the stellar mass to the halo mass as a function of halo mass. And if all of the baryons associated with that halo have been turned into stars, then you get 0.2 in this plot. And you can see that it's an order of magnitude at least below 0.2, and it peaks roughly around Milky Way mass galaxy. This is kind of the scale of galaxy formation, most efficient. And then below that mass or above that mass, it's an even smaller fraction of the baryons have been put into stars. And so something is happening. Like some of this gas that has cooled on the galaxies has been flung out of galaxies. A lot of this gas that has cooled has been flung out. Or the feedback it has before it could fall in and push the gas out. And exactly what scale the gas has been pushed is not something we had good probes of. And so in particular, there are various probes of diffuse gas in the universe. Unfortunately, the gas between galaxies is very diffuse, so it's hard to see. And so this figure just enumerates some of the different probes that we have with diffuse gas, and all of them are super messy, I would say. For example, hydrogen, H1 column, you might say, most of the universe is hydrogen, this one's potentially nice, but the hydrogen is highly ionized, so there are large ionization fractions. And also, hydrogen only exists in H1 if it's around 10,000 Kelvin. And this gas around galaxies, we can shock these kind of to the very low temperature of the halo, which is for a Milky Way mass galaxy something like 1 million Kelvin. So you don't expect a lot of hydrogen from the gas on the halo scale. And this is really cold clumps within halos. And then we have oxygen turns out to be better for hotter gas than super messy to that amount of baryons. Thermal SC people have done with Planck, but it turns out that the two halos that dominate is for smaller than group size halos. And so we just really don't know how far the bulk of the baryons have been pushed out around galaxies. Okay, so this is like order 1 seconds. So then you might say, but maybe we have simulations, and maybe they all predict the same thing, and so maybe this is not something that we really need to observe. And so this is the movie I love. It's of the illustrious simulation, and like the process we're talking about are these the explosions. So in this simulation, the galaxies they look like they're exploding, and so maybe and so the question is, do we really know how this works? Do we really know how to explode galaxies when they form stars? And there are arguments you can make that this is pretty hard to capture. So you need stars. You need to simulate where stars form in the universe. Turns out how much energy makes it out in the circumflex region outside of the galaxies. It depends very much on the density of the gas of the stars that are going supernova, like the supernova ejected get allowed into, because that affects how much cooling there is. So it depends on the feedback processes before supernova happen. It depends on how stars cluster, and so how supernova cluster in your galaxy. For more massive galaxies, it depends on supermassive black holes. It depends on the plasma physics and the magnetic fields and the mixing of hot and cold things in the circumgalactic medium, like how exactly the gas responds. And so you might argue that these simulations maybe this is something that's pretty hard to capture.
So what do you mean that black holes become? Are you talking about the stellar supermassive black hole at the center, or just
or the kind of the canonical picture in this field is that above Milky Way mass halos, when galaxies start to turn red and not have much star formation, that might have something to do with the formation and or the accretion on the supermassive black holes and the kind of the feedback processes associated with that. It also might have to do with the fact that in bigger halos, cooling is less efficient. And so even like if we went back to the initial picture, I'd say that like a big order one question is like why are some galaxies red and some blue? It depends on feedback processes. It depends on how the variance has been pushed around. And this is not totally resolved. Okay. So then and so this is kind of an interesting plot that so there were a bunch of CMBS4 collaboration white papers due earlier this week, and so one thing that they're trying to measure, this is going to be the competitor for FRBs, but it's hard to go to low halo masses like FRBs. I'll show you might enable. So one thing they did is they compiled a bunch of these numerical simulations for what they predict for the profile of gas around galaxies. So this is kind of a bigger halo. You're bigger than the Milky Way. Milky Way is 10 to 12 solar mass. And you can see that they predict way different things. And in fact, even if I did the interval over these curves out to, this is the virial radius, so this is 3 virial radius. And so in some of these simulations, the interval is not, it's not like the total mass is conserved with out to 3 virial radius. And some of these simulations are kicking the gas out really far. Which is kind of amazing. And this is a compilation. I think simulating this should only be harder for Milky Way mass halos because the cooling is just time scales are just much shorter. The cooling time scales are kind of getting comparable to the Asian universe. But and this is a compilation of models for kind of what the gas might look like around Milky Way mass halos. So like we don't know at order 1 the gas how the gas fits around these. Around galaxies, and this is a large fraction of the gas. And this I also would say is the missing variant problem. Like variants haven't disappeared. We see all the variants in the same beam, and one level force. They haven't disappeared, and this is what we don't know is how they've been pushed around that feedback from galaxy formation. Okay, so that's the motivation, and so now fast radio goes. Okay, and so I'm not ignoring the intrinsic contribution of dispersion. There are ways around this, but I'm first just going to tell you about the intergalactic contribution. And when I say intrinsic, I mean the host that's associated with the host galaxy or the host system. And so we have the FRB, and its light goes through the plasma that is the universe, and then time detects it, and like many of these. And depending on whether the light is going through dense regions of the universe or less dense regions of the universe, this will lead to like scatter. If I can calculate the probability distribution of the dispersion, this will lead to scatter.
But the scatter should never jump to it should become narrow when you go to large distance, right? Because
yeah, that's right. So the scatter will become smaller as you go to higher redshift. Partly also because there are just less of the gas in maidens and halos at higher redshift. So the universe is less inhomogeneous at higher redshifts.
This could be a Gaussian scatter, or is that just zero?
No, it actually tends to, because sometimes you go through a big halo. And so that's what dominates this. Okay. And yeah, so this is a good question. And this kind of leads to, what is dominating scatters? Is it the large things? Is it the fact that sometimes I hit a galaxy, a galaxy halo, which is small on this image, this is at a really large scale. So what is contributing to this scatter? And so there's a way of framing this. If you're a cosmologist, everything goes back to the power spectrum. And this is power spectrum of electrons. And so what's plotted here for the cosmologist, something like k² power of electrons. But if you're not a cosmologist, just think of this as like the integral over this. The red and one of these blue curves is kind of the variance of dispersion that you measure. And so this is telling me what scales the dispersion is coming from. And so there's some contribution that kind of comes from 50 megaparsec scale-ish, but pretty broad scales in the universe. And then this is the cosmic web, and it tends to be very small or smaller relative to the contribution from just hitting halos. And so the contribution from hitting halos looks something like these curves, depending on whether I push the gas really far from halos, like a couple of radii, or I keep it more compact. And so the variance of the dispersion measure is telling us something about how many halos I intersect along my path from the FRB to us. And this is the intergalactic component of the dispersion measure. And another way of thinking about this is I can just calculate out to some redshift how many halos I intersect within the Bureau radius. This is kind of the scale of the dark matter halo. If it's a 10 to 10 solar mass halo out, and let's do this for redshift 1, just to choose the redshift, then I'm hitting almost 20 10 to 10 and above mass halos within the Bureau radius. If it's 10 to 12 of Milky Way mass and above, then I'm hitting a few. If it's 10 to 13, I'm hitting 1. And this is the square root of n over n. This is the Poisson. Sometimes I hit a few halos, sometimes I don't. That's dominating the probability distribution of dispersion. Okay. And so there are two ways you can calculate this. One, you can run a lot of cosmological simulations and put in different feedback descriptions. A way that has a bit more freedom is called the halo model, which is kind of our most successful nonlinear model for large-scale structure, which decomposes correlations between. Is a model that has the halos cluster like matter, or as a bias tracer of matter on large scales, and we know how that clustering works. And so they trace the voids and filaments in the universe. And then on small scales, it's not the clustering of matter is dominated by the profile of the halos. So you can break down a model that really easy for how things cluster with that decomposition. And so then, what are we talking about? This model, I'm going to assume different profiles for how gas sits in these halos. And so, for example, if the gas is more diffuse, it's been pushed out further from halos, then my model might look like this, and if it's more compacted, like this. And if it's more diffuse, like maybe here the distribution is twice as large as this, then I'm hitting 4 times. If I made the radius twice as large, I'm hitting 4 times more halos. And so the square root of n over n is going to be smaller. So it's going to be less variance in the dispersion measure. Should probably not use dispersion in the dispersion measure. There's going to be less variance if things are more diffuse. So the variance have been pushed further than less one. All right. But I'm gonna calculate the PDF in a second. You always you start to calculate the variance as you use this thing, which is kind of the width of this PDF. And so this is the kind of the mean of the PDF. So this is if the universe were homogeneous, so you averaged over a lot of utilizations of FRB and a certain redshift. This is what you measure for the mean dispersion. And then this is the standard deviation dispersion. And I've only shown a couple models. And this is I also have done this in a simulation with some caveats. But one thing that you should note is that at redshift 0.2, like this is the redshift of R1, the repeater. The dispersion is like comparable to the mean. So like so I don't know if you can say that any of it like some of the dispersion is intrinsic or not. Like almost all of it can be intrinsic or almost none of it. Okay, and it turns out. And so people had developed this with clusters. You could in the halo model, you could really calculate the probability distribution of things in this model. And so with some kind of and it's kind of neat borrowing of equations and translating them to this application. This is the probability distribution we expect for different models. And these are just kind of like imagined models. I think we could do better. So for example, these are models where the baryons are a top hat extended to half a virial radius, 1 virial radius, 2 virial radius. And so you can see that if the distribution of baryons is more compact, then I'm intersecting fewer of these halos, and so there's a wider distribution, more of a tail. And then as the things become more diffuse, the distribution becomes more compact. And eventually it converges to this large scale structure part that should be variance. All right, and then this is a case where I assume that the distribution traces the NFW profile, which is the profile of the dark matter, and then I say below some mass threshold, they're very diffuse. They can push down very far. And so these are toy models, but there's some motivation for them. But at some level, you should take them with a grain of salt. But I do think that there's kind of this level of freedom in the observation. And then this is just doing it in the simulation. The simulation forms a lot of stars. So the mean distribution is somewhat low. Okay. But the problem with this is, it's fun to calculate, but there's no way to really, unless I can convince myself that the intrinsic contribution, the host contribution to dispersion is small, which maybe I can do if I had really high redshift forces. But if I can't convince myself of that, then I can't measure this probability distribution. And so I can't constrain these models from measuring the probability distribution of dispersion. And so there's a way around this, and the way around this is what I think is really a way to go, which is to when you find when you have an FRB and it's localized. And ideally, you know what the redshift, you localize it to a galaxy. Then it's more noisy if you don't. You don't have to. You have to localize it to less than an arc minute or so. But ideally, you have a galaxy to do this. And then you look along that sight line for all galaxies that are associated with stacks based on, like, for example, the stellar mass of the galaxy. And you might not even have to look because this is the era of these large photometric systems. So you might just go into LSST database and say, here are gay galaxies that are near the sight line. If it's high enough redshift, then the ODC redshift. Okay, and so then, so what this shows is this is the NFW profile for 10 to 12 solar mass halo. And this is the top hat model for where the baryons are distributed on 1 virial radius, and this is 2 virial radius. So this is the dispersion. And then these hatched dashed lines are if you have 100 or 1,000 redshift 1 FRBs. Assuming, so the assumptions are very important. And it's assuming that at redshift 1 you're dominated by the variance from the intergalactic medium, and not the variance in the dispersion that's intrinsic to the host. Now the variances in dispersion add a quadrature, and so if you had the same contribution from the host, then the variance would be a square root of 2 larger, the standard deviation would be a square root of 2 larger. And you can extrapolate any way you want. So it's easy to extrapolate depending on what assumptions you make. And so you can see that for 100 to DM at redshift 1, you're starting to be able to constrain some of these models. You would definitely detect it if it traced in a W profile. And by the time you have 1,000, under these assumptions, you're doing really well. And so this seems like these numbers seem within sight.
Actually, you can do without and 1 arc minute.
Sorry, where are you?
That's your sentence. One redshift of focus with tips to reduce noise. You can do without
Okay, oh, sorry.
1 half minute. What does that mean?
Yeah, this is the last thing I edited. This, I think, yeah, it's nonsensical. But so basically, let's say I didn't have let's say I localized a half an argument, which is kind of this scale. If this is ever just a half, then I wouldn't, if I didn't know the redshift of if I didn't say, oh, it's in this galaxy, and so I know its redshift, then basically I'm using the distribution of all my FRBs, like which might have depending on your survey, but will trace kind of the redshift distribution of the dispersion measure will trace the redshift distribution of all of your FRBs, which will have a broader, will be much broader than if I can say, oh, it's in a host galaxy. I can subtract off the mean dispersion, and then the error is now coming from the variance around that. And so your variance that you're trying to beat down the square root of n is going to get a lot larger if you don't have a host galaxy identification. But it's not, and so I think these numbers will probably will have to go up by a factor of 10 or 100 if you don't have if you don't say it's in the galaxy.
If you don't know the redshift galaxy.
If you don't know the redshift of the galaxy.
So this curve is knowing the redshift.
Knowing the redshift, and then there's a lot of other things. Here I'm assuming redshift 1. If we put it down in redshift, like it might get a little bit better, and so.
But get better.
Yeah, because then then the galaxy is contributing more the standard deviation dispersion is gonna be less. Like if there's a 0.3, and this one galaxy down the sight line is gonna be more of the total dispersion. Yeah. Okay. All right. And then, since a lot of people here are involved in time, I was kind of trying to brainstorm some very poor localization science. And as one poor localization science you might be able to do is M31. It's comparable to Milky Way size in mass, and so its halo its diameter should be something like 500 kpc. And so the halo should be something like 40 degrees on the sky, which is about 3% of the sky. And so roughly, like kind of following through on the similar numbers to the previous slide, if you had 10,000 FRBs over the full sky, better over a more localized region that includes M31, then you could potentially measure the distribution of baryons. And then you could also do this because for the local group, because the only thing that correlates in dispersion of your randoms of all of your sight lines is our galaxy. So
what is the DM of M31?
Yeah, it should be like something like 100.
100.
Yeah, it depends on the model. So the DM across.
Yeah, so if you, the top half put all the.
Yeah, something like 100. Yeah. Okay. Okay, and then I'm just briefly going to talk about scattering. And so some of your sight lines are going to go through galaxies along the way, and we have a pretty good idea from studying each one how many sight lines will go through galaxies. And because when a sight line goes through a galaxy, we call that a damped line analysis. And so if you just really naively say galaxies have the same scattering measure as looking out from the sun out of the plane of our galaxy, but then put the intervening galaxy redshift to half, you'll find that you get order 100 millisecond scattering. And so if your sight line goes really close to the galaxy, it's the pulse is going to be very scattergun. But we know that damp line alpha systems are not very are regions further out from the center of galaxies. much more likely than regions like the distance from the Earth to the center of the Milky Way. There's often the projection between the center of the galaxy and where we see the environmental system is many tens of kiloparsecs. And so probably the scattering measure is going to be less. And there's an estimate just based on kind of empirical scaling that I take with a grain of salt that the scattering might be something like a millisecond. But we know that about 10% of sightlines only will be affected by this. Only 10% of sightlines will be DLAs. And so the scattering that we're seeing for FRBs is very unlikely from going through intervening galaxies. And then even more unlikely is for it to be MHD turbulence in the CGM and IGM.
So not MHD, just cosmograph. So one and go just assume cosmograph term, not MHD.
Well, no. But you need the cutoff scale to be really small.
No, you need the atmosphere to be the order of that.
But this is diffractive, so the inner scale has to be smaller than the Fresnel scale, and I think that requires.
Oh, just assume cosmograph spectrum. But you assume that the power of situation goes like 4 power in frequency. This is just cosmograph scale.
But the mean free path of photons without the particles in your plasma is much larger than the Fresnel scale. So you need the Kolmogorov cascade to be on much smaller scales than the mean free path of your particles, and so I think that requires that you have MHD turbulence.
But MHD turbulence give you a different spectrum. It's three halves instead of 5 thirds. So,
but I think all of this, so all of the like even scattering in the IGM, which I like, this is a topic because I know Wei thinks a lot about this, and whether it is it is turbulence or whether it's something else. But like in the okay, well let's talk about this later. Okay. Okay, so but I guess I think so for this the assumption is just that the cascade is going to small like smaller scales than the Fresnel scale. But even if you do that, and you make very optimistic assumptions, and I would say that probably most of the IGM is not turbulent, but like it's very hard to get anything efficient.
Their argument is that you need so the outer scale in the cosmograph. If you see cosmograph turbulence, then the outer scale is to be very small. And if this is the case, then the dynamic time of turbulence is also very small. So if you in order to get the right scattering pressure, you need to double the temperature of the IGM every few months.
But I think that
this doesn't happen.
But I think that the IGM is so this like the fact that they chose the IGM and took the means into the IGM, I already fine.
I think you're both saying it's not going to happen. I'm not sure that the details matter so much.
But I would say this is much more likely. This is denser and much hotter and can cool much faster than this, and it's also turbulent. And this is not. So I actually think that their argument. I mean, it just seems very unlikely that you have anything like that.
To make 12 orders of magnitude, right? You need to go from the 1 parsec to the megaparsec. So there's a magnitude. So it's from 1 AU to megaparsec.
But I just think the heating of the IGM and turbulence is kind of an irrelevant thing. Because I don't think that's the situation that's more likely. So you're going through a lot of these CGMs, and it's a much different situation that's able to cool much faster. Okay, but this came out this week, so I was like, I thought, all of the scattering has to be intrinsic, and this is probably the case. Intrinsic to that part. But there is this idea that in the circumgalactic medium you have this 1,000,000 degree and sometimes 10 million degree plasma, and it can be very thermally unstable. And so there's an argument that you have thermal instability and there's condensation, and then there's a particular scale that's kicked out by the droplets that condense and cool to 10 to the 4 Kelvin, which is a stable temperature. And in particular, these people have shown, this is McQuinn 2012, and these are with hydro simulations. And kind of one thing that you have to assume is that conduction is shut off by plasma instabilities or magnetic fields. But if you just run hydro simulations, you find little droplets that are about a parsec for CGM conditions, which are set by how far a sound wave is able to travel in a cooling time. And so, and there's some observational indications that there are these parsec scale droplets in a certain class.
If you have these droplets that are very cold and very dense, then the optical depth, then the free absorption is very high. It's going to be very high, right? Because it goes like T to the minus 3 Hz.
But so very dense is still way less than -8. So
it's very cold also, right? And the absorption also scales very strongly with the temperature.
It's 10 to 4 Kelvin. So I would be surprised if let me just
You're talking about very low frequencies also, right? And the absorption scales like the frequency the frequencies to power -2. So it's not obviously. So it could be that it's not only visible.
Okay, I will bet you $100.
I mean, it's a partial equilibrium, and the temperature, meaning n is bounded by 0.2. I mean, no.
Okay, let's have this argument later because I can't do the 3D optical depth calculation at the moment. So the kind of the idea here is that the mass fraction in these things can be, the observation suggests it's very high. It could be something like 10% of the CGM. The volume filling fraction then is if there are 100 times more dense than the background is something like 10 to the -3. And so if you calculate the variance in electron density is much higher than the turbulence variance. And so you can have a refractive scattering off these clouds. And these people argue that the CGM could give you millisecond time scale the scattering. So I think this is interesting. So and you would expect, because things get denser at high redshifts, that the higher redshift FRBs are more scattered by the CGM.
Well, we think that this process would be more abundant during the feedback epoch when you're blowing the boundaries out of galaxy.
Yeah, and that also argues for redshift 2 is the epoch of star formation. So I don't know. I feel like this is something to pay attention to. And when you're looking at your scattering, when you start getting really large TM, and if it goes near a big halo, then in this picture you can start seeing a lot of scattering. And so we'll be able to test whether this is the case. And this constrains the size of these droplets. If the droplets are bigger, then the effect is smaller. Okay. So that's all I had to say about the circumgalactic medium, finding the baryons and understanding the processes going on in the CGM. And so now I'm going to change gears and talk about cosmology with FRBs. And I would say that I'm going to discuss 3 possibilities. One I think is pretty straightforward, but not very exciting, maybe not as exciting as the other possibilities. And 2 of them we're going to probe kind of what is required, like how all things have to go in order for us to really be able to constrain cosmology. Because we're in this era of very precision 1% cosmology, so we have to constrain potential systematics to much less, to a percent or less. Okay. And so the cosmology option that has been mentioned quite a bit in the literature, but maybe is the most optimistic, is to measure the mean dispersion as a function of redshift, and be able to separate the dispersion that comes from the IGM from the dispersion that comes from the host system. And in particular, in order to do cosmology, this part from the host system better be about 100 or less of the contribution of the IGM. And so I think in the best case scenario for this to work, I would be comfortable if we started finding FRBs that are a little bit outside of their host galaxy. Then maybe we know that there's not much intrinsic, and we know that there's the DM from associated with the system itself is also small. Perhaps if we confirm that this magnetar model is very presented by then. And so if we start finding a lot outside of the host galaxy, and then they can't be too far out, or we're not going to know what galaxy to associate them with. And then the other thing that we need for this to work is that we need because the IGM has a lot of scatter, we need to measure the mean of this to 1%. The mean dispersion to 1%. Then if we're measuring FRBs at redshift 1, you still need about 1,000 FRBs. So we need 1,000 FRBs that look like they're not being absorbed by the host galaxy ISM. And we need to also know that the DM intrinsic for the system is less than 10 parsecs, something like that. And then I think we might be okay.
At 1%, don't you know how many variant and stars to like?
Okay, I had that caveat before too. So then I think around the 1% level, I started at the 2% level. I get nervous because before I said 4% are in stars, and I would say it's probably like 4 to 6, maybe 4 to 8%. But maybe we figure that out. We do have people are studying the stellar mass of galaxies with different amounts of lensing, So I think that we can get that to 1%. But you're right. So there's even another if that we need to know the amount of variance. And then even maybe makes me a little bit more pessimistic. Brian Ginsler and some others have shown that even if you have 1,000 and you know that this isn't important, you still aren't super competitive for dark energy districts. They really did like an Fisher analysis. Okay, so then option 2 is that we start building bigger and bigger FRB telescopes, and I've seen millions of FRBs with localizations, and then this becomes very similar to a weak lensing survey, because then so weak lensing you're measuring the shear or possibly the magnification of your galaxies, and that's telling you about the projected mass with some kernel. Here the kernel is different, but it's essentially the same. It's telling us about kind of the projected density of invariance. And so then I kind of back of the envelope what I think what this would require. I'm not going to go into the details, but I think so for weak lensing. So in order to be competitive, weak lensing we have 1 billion galaxies, and so what sets the noise is the intrinsic ellipticity of these galaxies. And we're looking for a 1% signal. And then what sets the noise for us is different. And so if you go through those numbers, things are a little bit better. Like you're not looking for a part in 30 potentially. And so maybe, and I was being very optimistic, maybe you could get away with 10 million. And then you're doing, you have different systematics than we can do. Maybe it's even better. But you need a lot. Okay, then this is the most safe and likely cosmology, which is, it turns out, and it's kind of for reasons that aren't totally obvious to me, that maybe I shouldn't say this, but that the cosmology community has invested very significantly in doing weak lensing. And so most cosmology surveys in the next decade, or many of them, are finding billions of galaxies, measuring weak lensing. And so these are some of the surveys. So this is the era of weak lensing. And so there are a lot of systematics for weak lensing, but maybe one of the ones that if we measure the redshifts of the galaxies as well as we can, the flow disease is one of the issues. But you know, with infinite telescope time, we could probably measure that as well as we need. But eventually, like we're going to the bottleneck is going to be that we just don't know where the variants are. And in order for these weak lensing surveys to meet the parameter forecasts that people made a decade ago, you really have to go to pretty high wave numbers. And so the wave numbers that we want to use for these weak lensing surveys to really advance dark energy constraints are kind of higher than current models for where the baryons live allow us to go. And so we need a better model for how the baryons are being distributed. And that fits into the first part of this talk. And so if we measure where the baryons are, then that's getting us some of the way that we need to go. And then it's going to be on the galaxy modelers to understand the response of the dark matter to the distribution of the baryons. And so FRBs, by measuring the distribution of baryons, is giving us an input to these models where then we can say, this is the effect of baryons on the power spectrum of matter that the weak lensing measures, and that's going to be really helpful for pathology for weak lensing. Okay. And then this is my final slide. So kind of interestingly, in 2014, so kind of the standard understanding was that that you needed a transient source to measure dispersion. And then there were a bunch of studies claiming that no, that's not the case. If we measure higher order correlators of the electric field, then this has the information about dispersion hidden in it. And so the reason this is not the case, and then in fact it turns out that there was one group that was building an instrument to detect one of these statistics, and there were a couple using radio data to apply statistics that had been suggested. And so but the reason that this doesn't work is really pretty straightforward. And it just all boils down to the fact that how dispersion affects things is by adding a phase to the waveform. It's not affecting the energy of, like for example, Thomson's scattering, the energy of my waves. And so because it's not affecting the energy, it's just adding a phase. But as you might then immediately realize, if it's just a phase, and then if I had some incoherent source, then I had zillions of electrons contributing. And in our paper, we even do an estimate for how many electrons for typical sources. And so that this means that the waveform is going to be super Gaussian. The electric field is going to be super Gaussian. But then if it's super Gaussian, by the super limit theorem, I'm just not going to be able to detect the phase. And then in this paper, we also talk about other things with sources. But it's not like major sources that might not be Gaussian. But nothing seems to work. And then in this paper, we also show that this holds in quantum mechanics. And so the conclusion is that we need FRBs to measure dispersion. There's not some easy way to use AGN.
So what was the argument in those three papers? Did they just make an error, or did they?
Yeah, they made an error. They were calculating a 3 and 4.4. One of them was calculating 4.4 to the electric field, and didn't do the calculation correctly. Another was assuming that quantum mechanics made it so that when I observe the photons in my dish, but then it's kind of the effect of quantum mechanics is kind of like a Poisson. They put in the effect of quantum mechanics in a very weird way that that was so there were various mistakes. This paper, I give you a two-line explanation. This paper is like 20-something pages. The appendix is like, I don't know, kind of my co-author is like ridiculous quantum field theory and showing that coherent states of the quantized electromagnetic field, which are the kind of the classical analogs of the eigenvalues are kind of like our analysis of classical waveforms. have all the information in the quantity, blah blah blah. So if you're interested in a long read, but the explanation is there for the classical part, for the quantum mechanics. Okay. And so my conclusions are here I'm pretty optimistic. So no matter what FRBs are, I think it looks like we'll be able to once we're able to localize enough of them, be able to use them to map the baryons. And this is really interesting. This is an order one question in cosmology and galaxy formation that we haven't answered. Cosmology with FRBs, especially just FRBs alone, is going to be really hard, and we're going to have to get lucky. Although, if we know where the baryons are, we're really investing a ton in cleansing. That's going to be a tremendous help. Thank you.
Any questions for Matt? Wait.
I thought Kendrick was going to ask a question he hasn't asked yet. So when you say mapping the baryons, obviously they are great, but how does it compare on like the CMB is supposed to also map the kinetic SZ and other things that like on what do you have to do for this to be interesting?
Yeah, okay, that's a good question. This is the S4 prediction for how well from this KST stacking we can do on 10 to the 13th solar mass. This is the virial radius, and so I think as we go to lower mass halos, it's going to get I haven't seen the S4 prediction for 10 to 12 solar mass, but it starts the resolution for your instrument is going to be kind of comparable to the virial radius of like kind of a galaxy survey that you might stack. And so for lower mass halos, it's going to be harder for the CMB to do this. But yeah, this is a good question, and I think I'd like to see the S4 people do the same calculation, but for 10 to 12. But for FRBs, you can potentially even do 4 galaxies. So we can do this. The FRBs are going to be able to do this at lower halo masses than S4, but I don't know where the cutoff is. If S4 is going to get to 10 to 12.5 or 10 to 12, okay. Do you have a feeling for where a KST stacking is cheaper?
So do I interpret you two plots then that 1,000 localized FRBs are as good as CMB S4, roughly, for going after the baryons?
Yeah. And this is for 10 to 13. I think this is a compare. People need to do these calculations. I think it seems like this is about right. And then at 10 to 12 solar mass, I don't even know CBS can do it. So for like
yes,
for the
of course, and then you can beat it completely with more FRBs and localization. So, in other words, the potential is it's easy to catch up to S4, and it's possible to completely outrun it by having, say, 10,000, 100,000 localized FRBs.
Yeah. Get FRBs.
Localized.
Any other questions?
Yeah, so I had a question about your discussion of the additional scattering contribution to being scalable.
Let me go ahead.
You mentioned it last week.
Oh yeah, it actually came out this week. So I haven't had a chance to fully read it.
But you mentioned that this effect would cause an additional scattering contribution, which would be in
yeah, I mean, I think it's very model dependent, but where I think the evidence is the best that that this is happening is kind of bigger halos, like maybe 10 to 13 solar mass halos that I mentioned too, where we just see a huge amount of line alpha emission, and it seems like the gas is really fragmented down. But there's in this paper there's quite a few suggestive observations that things are really fragmented down to close scales.
But at high rate, what you have to take into account the strong frequency dependent
Oh yeah, this is at 30 centimeters. So yeah, so if you're doing this at lower frequencies, the scattering time scale is going to be a lot longer. So it's going to be literally about 4.
I mean, that one can answer with existing data, because, for example, in 110523, we know that the scattering did not happen in between from scintillation. So I think just by looking at scintillation properties of existing bursts, one can limit what fraction could have been due to this.
Yeah.
Or conversely measure how many fractions. So what this predicts is scattered object events that do not scintillate.
The distribution of the scattering, or the distribution of that's related to the shape of the distribution, not related to the level of pumpiness.
Sorry, is
it related to the level of pumpiness of the class medium?
For the scattering, or
for the scattering, or for the dispersion?
Yeah, the scattering is determined by the pumpiness of the, so it's an n-squared process.
Yeah, you're looking to get out large outlier, highly scattered events. More pumpy.
Yeah, that's right, and that's why like cosmograph, like the outer scale things tend to be like, they're never grossly supersonic, and so the variance is never super high. Whereas here, to calculate the variance of the density, and you're filling 10 to the minus 3 of your halo with something that's 1,000 times more dense, then your variance is 1,000. So you can get because of how pumpy this situation is. You have hot gas and you pressure confined full gas. That's what's making it so that it actually makes you can actually get a lot of scattering.
Any more questions? So if not, let's thank McQuinn.